Every living thing on Earth relies on the same biological engine, the cell. It is a highly efficient machine, constantly absorbing nutrients, producing energy, and keeping you alive. If this engine works so effectively, it raises a question. Why hasn't evolution scaled it up? Why don't we see single cells the size of a basketball? It is tempting to look at a microbe under a microscope and assume its tiny stature is just a biological coincidence or an evolutionary fluke. But cells are actually restricted to that microscopic scale by an invisible, unbreakable physical barrier. A cell's microscopic size is a highly tuned adaptation, strictly constrained by the brutal laws of mathematics. The mathematical governor of all biological growth is the surface area to volume ratio. When any physical object grows, its surface area naturally expands, but the internal volume multiplies at a cubic rate, filling the space inside much faster than the surface keeps up. This gap creates an unavoidable mathematical rule. As an object gets bigger, the ratio between surface area and volume plummets. This geometric reality creates a hard limit, dictating the exact scale at which biology can safely operate. In a living cell, that surface area is the outer membrane. It acts as the strict gateway for every single resource trying to get in. The volume is the cytoplasm inside, the internal factory that constantly consumes oxygen and nutrients to sustain life. If a cell were to grow to a macroscopic size, its outer membrane would become mathematically insufficient to supply that massive internal factory with the raw materials it needs. At the same time, the factory is producing metabolic waste, like carbon dioxide. With a proportionately shrinking membrane, those toxins cannot exit the cell fast enough. Even if materials could cross the barrier, the vast internal distances of a giant cell mean that internal diffusion would slow to a crawl, leaving the center of the cell effectively cut off from the outside world. When a cell ignores its surface area to volume ratio, its internal logistics collapse. It starves and suffocates within its own mass. This physical constraint is the very thing that gives cells their greatest competitive strength. By remaining microscopic, a cell maintains a perpetually massive surface area to volume ratio, ensuring the membrane can always effortlessly service the small space inside. This enables blistering speeds of metabolic exchange. The cell can pull nutrients out of its environment and fuel its internal processes almost instantly. Prokaryotic cells, like simple bacteria, are the true masters of this rule. They use their extreme smallness to maximize their environmental interaction. This efficiency allows them to grow and reproduce at astonishing speeds, sometimes doubling their entire population in less than 20 minutes. This generational speed is the engine of evolution. In the time it takes a larger animal to produce one offspring, a colony of bacteria can cycle through thousands of generations, providing millions of opportunities for beneficial mutations to solve new environmental threats. The mathematical advantage of being small creates a metabolic engine that can outpace almost any environmental shift, making the microscopic scale the most resilient architecture in the history of life.